Okay, so good afternoon. So last time we end up with the discussion on the valence electron, the core. We end up with silicon crystals as well as the maximum saturation. When the valence electron reaches number 8, it becomes chemically stable, and therefore the sharing of silicon atoms are bounded to each other, no? They are chemically stable. Now we'll proceed now with the next topic, okay, and that is the two types of semiconductor materials. So let me just give you an idea. For a semiconductor, no, we have two types of materials. The intrinsic, okay, the intrinsic semiconductor, and as well as the extrinsic semiconductor. So as I said last time, an intrinsic semiconductor, an intrinsic semiconductor is a semiconductor which is actually pure. So ibig sabihin, meaning to say it is pure, it has no other impurities. While extrinsic is simply a pure semiconductor added with impurities. So what is the difference? As I mentioned last time, if the semiconductor is simply pure, therefore it is more of an insulator. Okay? So if it is pure, it is more of an insulator, meaning to say the flow of current is not possible. But to make it more functional, to make your semiconductor more functional, allowing the flow of current, then make it more conductive. So extrinsic simply means you're making your semiconductor more conductive, and that's the reason why we have to add impurities to it. Okay, so let's proceed now with this discussion. So this is an example of the silicon. Okay, the disadvantage of intrinsic semiconductor, simply at room temperature, it has equal number of free electrons and free number of holes, which will not make any movement at all, or meaning to say there will be no movement of charges, and the semiconductor itself is like an insulator. Okay, next, if we're going to proceed, so also I have mentioned last time, say for instance these are different types of semiconductor, okay, and they are sharing now electrons. Okay, so if we have a hole here, the electrons here, which is negative, and hole acts like a positive, the electrons will be attracted to the hole. So electrons will move to the left. Once the electrons moves towards to the left, the space where the electron occupies becomes vacant. Thus, it becomes now a hole. Okay, if this a hole, this is a hole, and this is electron, definitely the electron next to it will get attracted to this hole. So meaning to say there will be some attraction. So these electrons will merge or recombine with this at point A, and then this becomes a hole. Also, the same thing happens since this is now positive and the next electrons is negative. So what happens is there will be some attraction. So what can we see now? The hole is moving towards to the right while the electrons is moving towards to the left. So meaning to say the flow of your free electrons is always on the opposite direction of the flow of your hole. So this is what I was telling last time. Previously, we have two types of semiconductor, the intrinsic, which is it acts like an insulator, so meaning to say you cannot current cannot pass through. So if you want to improve the conductivity or letting the current to pass through, then make the semiconductor into extrinsic. So how do we do that? What is the process? So it is what is known the word as doping. So doping is simply increasing the conductivity of a semiconductor by adding non semiconductor materials, or simply by adding extrinsic. So once this impurities is added, it is now called as intrinsic semiconductor. Okay, so let me give you an idea. Say for instance, we have a pure semiconductor. The pure semiconductor is illustrated as a water. Okay, so say for instance, I have here a glass of water. Okay, and the water represents now the intrinsic semiconductor. Now, in order for it to be, in order for the semiconductor to be conductive, you have to add some impurities. So impurities may be represented by other materials rather than water, or that can be some sugar. So if you pour out the sugar here, so it will be mixed now with the water, then the water is no longer pure, but rather it is now a combination of a water and sugar. So it is now extrinsic. Okay? So that is the difference now. So intrinsic is a pure semiconductor, while extrinsic is a pure semiconductor with added impurities. Okay, let's go back. In making a semiconductor as an extrinsic semiconductor, you have two options. Either you increase the number of free electrons or you increase the number of holes. So that is what is meant by here. Making your pure semiconductor to an extrinsic semiconductor, either you increase the free electrons or you increase the number of holes. So how do you increase the free electrons? Okay, so that's the thing that we are going to discuss right now. Now let's go back now with the illustration. Say for instance, in making it, okay, sorry for that. Let's read first the lecture here. So how do we increase a pure semiconductor? Increasing the free electrons. Okay, so what does the manufacturer do in doping? First, it melts the pure silicon crystal. When the pure silicon crystal is melted now, the covalent bond breaks, and that changes silicon from solid to liquid. Okay, so once the crystal now becomes a liquid, that will increase the number of free electrons. Okay, and then pentavalent atoms are added. To increase the number of free electrons, you have to add a pentavalent atoms. And what are these pentavalent atoms? This is antimony, arsenic, and phosphorus. So you add this, you add this to the molten silicon. So these impurities, let's say, although only added 1 part in 10 million, that could already change or alter the band structure sufficiently to change the electrical properties of materials. So let me just give you an illustration of that. So I have to print screen this one so that I will no longer repeat the illustration, but rather have already the guide. So what you have right now is an atomic structure, a perfect covalent bond. This was already discussed last time. Okay, so our topic now here is we are under extrinsic and we want to increase. Now we want to increase the number of free electrons. Okay, so that is now our goal for this discussion. So in order to do that, first, as mentioned earlier, the solid crystal must be melt so that the covalent bond, the 8 valence, will lose its bonding. So after doing so, we will simply add an impurity. So as you can see, this is silicon. Now this is silicon, this is silicon, and that is silicon, and that is silicon. So what do we add? So to increase the number of free electrons, we have the option to add any of these elements. So P is for the phosphorus, arsenic, or antimony. Why? All of these are pentavalent atoms. So an pentavalent atoms has a valence electron. It has a valence electron of 5. That's the reason why it was called pentavalent. So let's count. So for the inner, obviously it has 4 valence: 1, 2, 3, and 4. Okay, because it is a silicon, it's a semiconductor. Next, for this one, silicon, it has 1, 2, 3, and 4. Next, for this one, it has 1, 2, 3, and 4. Next, for this one, it has 1, 2, 3, and 4. Now, we will take note on the phosphorus. What was added to this pure silicon is an impurity called phosphorus. And phosphorus has a valence electron of 5. So what happens? So the phosphorus now will have, okay, look at this one, 1, 2, 3, and 4. So the last orbit can only carry up to 4 since this is the material for semiconductor. So if it has 5 valence electron, the other electrons will stay outside. And it is now free to go anywhere. So if it is free to go, therefore this charge can now easily move. If it can easily move, then you are now making your extrinsic semiconductor conductive because it is now free to move. Okay? Now, let's proceed now with another. What about if you want to increase the number of holes? That's the next question. So, to increase the number of holes, what you have to do is to add a trivalent impurity to a pure semiconductor. This trivalent impurity was called trivalent because the valence electron is 3. An example of these are boron, aluminum, gallium, and indium. Okay? So, trivalent atom is also called an acceptor atom because each hole it contributes can accept a free electron during recombination. So, let me discuss what happens when we add, no? When we add another, when we add an impurities to a impurities with trivalent atom. Okay, so this time we are adding boron, and boron is actually an example of trivalent atom. Okay, so let me just discuss what happens now. Let me just enlarge my screen. There you go. So let me remove this one. So let us again check. Okay, so let me use the black. This is again. We have a silicon, a silicon, a silicon, and a silicon. So again, in a silicon, the valence electron is 4 because it's a semiconductor. 1, 2, 3, and 4. So that is the valence electron of the inner silicon. Next is the valence electron of the outer. 1, 2, 3, and 4. What about this one? We have 1, 2, 3, and 4. Okay. And silicon on the left side, we have 1, 2, 3, and 4. Okay. Now, what happens? It is obvious that what is added is boron. And boron is a trivalent. So, meaning to say, it only has 3 valence electrons. So, let's count now the valence electron of boron. We have 1, 2, and 3. Now, all of the valence orbit in this extrinsic semiconductor has 4 spaces for electrons. However, what is added is a boron which only has 3. So, therefore, that is an advantage because there will be a vacant space to fill out. So, this, what happens now? There is now a creation of what is known as a hole. Okay? So there is now a vacant space which is now a hole. And this hole now will create now attraction from this electron towards this one. Okay? So there will be a movement of electrons. Once that electrons recombine with the hole, this will be vacant. And meaning to say, this becomes now a hole. Okay? So another electrons will be attracted to this hole. It will simply jump towards this hole. So this will now be 8 electrons, okay? And next, this will become a hole. So what did you observe? There is now a movement of charge, okay? So if there will be a movement of charge, meaning to say, charges is moving, there is now the flow of current. Meaning to say, let's go back here. Meaning to say, whether we increase the number of free electrons or increase the number of holes, okay, both has an idea of creating movement of charges. So that is the advantage of making your pure conductor to be extrinsic semiconductor. And the process of adding impurities is what is known as doping. Okay?